And welcome Calculus 3 students. Today we are extending our double integrals to include double integrals in polar coordinates. If you will recall, when we went from rectangular to polar coordinates, we used these relationships here. We'll use those again. And our theorem allows us to extend that to polar coordinates, and it is a very familiar equation here. We have our function times r, and I'm going to integrate with respect to r and with respect to theta. So let's look at our first function, which is a volume sitting over here, and I'm supposed to find the volume of that solid, and my z would be 9 minus, and if you'll notice, this is going to be just r squared. When z is 0, then my radius goes from, so when z is 0, my radius goes from 0 to 3. So my integral will look like 0 to 3 for that dr. And for my d theta, those limits of integration is going to go from 0 to 2 pi. My function is this 9 minus r squared times my r, and then I'm just going to integrate and get this. Alright, after integrating that and plugging my limits of integration, I get 81 over 2. For my next example, it's one that we've seen before. We have our top function, which was that z equals 8 minus, and notice once again that is r squared. R squared, I'll fix that. And then this is going to be z equals r squared. And for my limits of integration, I need to see what my r ranges between. It'll range between 0 and this projection here, and if you'll recall, that intersection was that projection, and that was x squared plus y squared equals 4. We did that in example 5 of 14.2. So our volume here will be, my limits of integration are going to be from 0 to 2, and then I'm going to have the top function minus the bottom function. So that's going to be 8 minus r squared, and then minus this r squared all times r dr d theta. My limits of integration on theta are 0 to pi. I'm going to simplify this a little bit and integrate my first integral. Oh, I think I got carried away and went ahead and finished it anyway. I did my simplification here, and then I integrated, plugged in my limits of integration and integrated again, and this volume is 16 pi, which is what we should have gotten in example 5 of section 14.2. In our next example, we're to find the volume of this region. This is not quite as pretty as the others. Z is going to equal to, for my x, I'm going to insert r cosine theta. For my y, it's r sine theta plus 10. So that means my z is going to equal r squared cosine theta, sine theta, lovely, plus 10. Probably will be easiest if I'll use one of my double angle formulas here and just say that on the side sine of 2 theta is going to be 2 sine theta cosine theta. So I'm going to substitute here, and I'll say that r squared is this sine 2 theta over 2, because I was lacking a 2 in this, plus 10, and I'll use that as my z. So let's note what our integral needs to be. They tell me that they want me to cut this off on my r between 2 and 4, so I'll integrate with that, and my theta is from 0 to 2 pi, so I'll put those limits of integration in. I need my z equation here, which is r squared sine 2 theta all over 2 plus 10 times my r dr d theta. And now comes the lovely task of integrating this thing. So I'll do that. Let me go ahead and note here that I am integrating with respect to r. So that means that I'm going to get, oops, yeah, so let me fix this. Okay, let me try this again. So I'm going to integrate with respect to r, got the horse before the cart here, and note that this is r to the fourth. Now this sine 2 theta doesn't have an r in it, so it's just like a constant over, and then it's going to be 4 times 2, which is 8. So then I'll have plus 10r squared over 2, evaluated from my limits integration, 4 to 2, d theta. I'll plug those values in for r, and then I'll get what to integrate with respect to theta. Alright, when I get finished with that substitution, I get that that volume is 120 pi. Figuring out this problem is a big problem in and of itself. They're talking about a circle of radius 2, and then I have another circle sitting here, r equals 4 cosine theta. And what I'm supposed to do is write an integral for some sort of volume, and I'm not given what that elevation function looks like. I'm just going to write it as such. So what they're really asking me to do is figure out what your limits of integration are. So for your volume. So I've got to figure out what they're going to be for theta and what they're going to be for r, and I'm just going to write this as some function here that's an elevation function that I don't really know what it is, and this is dr and this is d theta. The first region that they want me to look at is this region here that is outside of my circle of radius 2, and it's outside of that but inside this circle where r equals 4 cosine theta. So my r values are going to range, and with this I need to figure out exactly what does that r range from. Well, that radius ranges from this 2, which is this lower limit here, to the 4 cosine theta. And then my theta values, I need to figure out where these two intersect. So that is where 4 cosine theta equals 2. So that would be where cosine theta is 1/2, and that is going to give me pi over 3 and negative pi over 3. And it's not really clear, but that's all they're looking for A. In part B, we're supposed to look at the region inside both circles of part A. So that's going to be this region here. And for that, I'm going to break that into 3 parts. It's going to be this part, this big part here, so it'll be this part, then this part here, and then this part. So that's how I'll break that up. Alright, so I've written this is going to be my first little area here, and this is my second area, and that will be my third area. So it's just whatever is shaded there. So my first area that I'm going to look at, let's go ahead and write this out, and it's just going to look like this on the inside, and the whole point of this is just to get my limits of integration. So my radius here is this red circle to 0, so 0 and then 4 cosine theta. The theta itself is going to go from negative pi over 3 to negative pi over 2. Then we're going to do the same game again. Oops, theta dr d theta. Let me write the other. Okay, this middle radius goes from 2 to 0 because he never really touches that red circle. There's his radius. And then for pi, on this one, it goes in between these two values here, so that is pi over 3 to negative pi over 3. And then for my last, I'm going to have that same limit for my r. It's the 4 cosine theta. He's on the red circle to 0. That's his radius. And his limit of integration is going to be this pi over 3 to pi over 2. And that's all they want for this problem. And this becomes rather nice if I am given everything in terms of polar and I'm to integrate for my area of these polar regions. What I'm to do, now I've got to figure out my limits of integration, and I'm just going to have r d theta. So let's see if we can get our limits of integration. They've drawn for you the area that you're looking for. So for my r, this radius is going to be this outside circle, which is, when I write this in just terms of r, it's going to be r equals the square root of that, which is 2, and then square root of cosine 2 theta. And then this bottom here, or this leftmost part, and that is a circle of radius 2. So since it's a circle of radius 2, I'll just write this as a square root of 2. And then I'm going to look at what my theta ranges from, and that would just be the intersection point of these two curves. And if you calculate that using this 2 equals 4 cosine 2 theta, you're going to end up with theta is going to be equal to positive negative pi over 6. So it will look like this. And now it's just straight up integrating from here, which makes it really nice. So I'll do that. And when you get finished plugging in all of your limits of integration, that would be what you got for that area. We're going to be finding the average value, or average y-coordinate here. They're going to tell us that what we need to do is integrate the function over the region and then divide by the area of that region. So let's just go ahead and get dividing by the area of that region. The area of this region is pi r squared. So since I'm talking about a semicircular disk, I only have half of this. The total area is that of a circle divided by 2. So since I'm supposed to divide by that area, I'm just going to write the flip of this. And then I am to integrate, and I will get my r dr d theta. Let's write down my limits of integration here. My limits of integration are ranges between 0 and a. And theta is going to just go between 0 and pi. And what does my function look like? My function is just, let's see, they gave me that, the y-coordinate of the points given by that. So the y-coordinates are y equals r sine theta. That's what my function is, because I'm supposed to find the average of the y value. And this is the y value, so I'm going to write that in as my function. So that would be r sine theta. And after this, I'll just integrate and get my values. And here's what I get so far. Now I'm going to plug in my limits of integration and integrate with respect to theta. I just noticed I didn't plug in my values for r, which my r happens to be a, so I plugged in an r. But anyway, I need to replace those with a's because it is held at a constant, not a variable. Alright, finishing up, doing my integration and getting that average value. There is the average value of the y-coordinates. And if you want to know what this is, that would be the average y value is 0.42.